Okay, so welcome back to the next lecture here. So today, what we will basically be doing is deriving or evaluating this integral to show that it is evaluating this integral to show that it is root pi. Okay, so this this particular integral is important when you are trying to find the average energy of an oscillator using the Boltzmann's distribution. So along with this one, there's also another integral that we have to prove here. So I'll also be writing that integral here. So we basically have to prove that x squared e to the minus x squared dx equals to root pi over 2. So we'll have to be trying to evaluate these two integrals. Okay, so that's going to be our job for the next 15-20 minutes. So let's move on with the first one. Okay, and it's fairly easy, so you don't have to worry that it's going to be difficult or something like that. It's going to be fairly easy. So dx. Okay, but we will verify it, or we'll try to evaluate this integral by some technique. Okay, and that technique is just trying to convert it into a polar coordinate. So let me say that this is I, and let me also say that I just written in another variable y here will be e to the minus y squared dy. Okay, so let us multiply these two. So can I write I times I is simply integral e to the minus x squared plus y squared dx dy. Okay, so what we have basically done here is reduced the or let's say more appropriately change the one-dimensional problem to a two-dimensional problem here. Okay, so excuse me, I have to write two integrals here, evaluated over two different variables here. So e to the minus x squared plus y squared dx dy. Okay, so this is our uh, the integral then. Now you may be wondering, how is this easier, right? So we'll see in a minute. Now before that, let's talk about a polar coordinate. So a polar coordinate is basically where x can be represented as r cos theta and y equals to r sine theta, right? And so if that's the case, then I can also say that x squared plus y squared is basically r squared, right? And so let me just substitute this here. So we have again now the integration over two integrals, right? So one has to go from, okay, let's just put two integrals here, but now we'll have to write e to the minus r squared. Now because dx dy is the differential area, so what's the differential area in the polar coordinate? So for that, let's try to look at this one. So let us assume that we have a circle, and let us take another circle that's just dr bigger than the initial radius. Okay, so this is r and this is dr. So if you want to find the area of this small increment here, I hope everyone do understand that the increment is basically 2 pi r dr, right? So dA is just that. So that means in the polar coordinate it's just this. But also, if you look at it in another way, you could also think of it like this. So let's say this is a part of a circle. It's a part of a circle, and we just increase this here like this. Okay, so this is dr here. Now let's say this is d theta, and this is r. So I can write the length here as r d theta, right? So I can write this as r d theta, and we have the small incremental in the dr as that. So now we can also say that dA is just r d theta dr. Okay, so you will see that both of these things imply the same thing. So in this above integral, then I can, instead of dx dy, I can write as r d theta dr. Okay, now r goes from minus infinity to infinity. Okay, excuse me. Yes, r goes from minus infinity to infinity, and theta goes from 0 to 2 pi, right? So now, if we just look at separating the variables, then our integral just simplifies to this one, right? So 0 to 2 pi d theta, it's d theta times minus infinity to infinity e to the minus r squared r dr. Now, so this integral is just 2 pi. Okay, and we have minus infinity to infinity r e to the minus r squared dr. Now, I hope you recalled that. Now, all we have to do is we have to substitute, and after substituting, we can simplify it to find the integrals. So let us assume that u is equals to, okay, so u equals to r squared. Let me just take it as minus r squared. So the u is just minus 2r dr. And so if you take r as minus infinity, u is minus infinity. So let's put it like this: when r equals to minus infinity, u equals to minus infinity, and when r equals to infinity, u is still minus infinity. Okay, so, oh, excuse me, there's a slight mistake here. The r has to go from 0, right? Not from minus infinity. There's a slight error there. Okay, so r goes from 0 to infinity, not minus infinity, because there's no meaning of minus here, right? So let me just put it like this: when r is 0, u is 0, and when r is infinity, when r is infinity, u is minus infinity. Okay, so then our integral then basically reduces to 2 pi 0 to minus infinity e to the u dot, and there's a minus sign there, so I'll just put minus minus du by 2, right? Because if I rearrange this term here, I could write this as du by 2 equals to negative this is equals to r dr. So instead of r dr, I've written that way. So now this just becomes then minus of pi integration 0 to minus pi sorry, minus infinity to the u du. Now we are almost at the end of the derivation here. So now what we can do is just minus pi integration. Let me just integrate and then put the value. So integration is just e to the u 0 to minus infinity, and this is just pi e to the minus infinity minus e to the 0. So this just gives us e to the minus infinity 0, so this just gives us pi, right? So then our final result is then I square, because we have been evaluating I square, right? So now we can just say this implies I square equals to pi. But our aim is not to find I square, but our aim is to find I only, right? So therefore I equals to root pi. So that's the evaluation for the first integral. Now I hope the methods that I've shown here was easy for you all to understand. Now without any further ado, let's move on to the second integral. And our second integral was basically integration of x squared e to the minus x squared dx, right? And we had to show that this is just root pi over 2. Now in this integration also we will use some technique to solve it, and I hope that technique will not be so difficult for you all to understand. Now let's say in this case let us just put y equals to e to the minus x squared. Okay, so then I could write this as dy by dx, excuse me, so dy by dx as minus e to the minus x squared dot 2x, right? So using chain rule and then substitution. So simplify this to 2x e to the minus x squared. Okay. Now let us differentiate it again so that we have some sort of pattern here. So if I differentiate this again, then do you all agree that we have this one? 2x bracket minus 2x e to the minus x square bracket close plus 2e to the minus x square. Okay, so what after this then? Now can I will simplify this as then 4x squared e to the minus x squared minus 2 e minus x squared. Now you might be questioning, are we integrating at all, right? So you'll see in a minute that when we integrate both sides, so now let me write like this then. Let me show you the thing that we had here. I can write this as d2y by dx2. Now integrating both sides. Okay, so I'll integrate both sides. Then we have integration of d2y over dx2. Obviously it's with respect to dx, so I'll write dx here equals to integral of whatever we have in the upstairs there. So x squared minus 2e to the minus x squared dx. Okay. Now again, because we need the integration from minus infinity to infinity, okay, so that's what we are basically looking at now. Now, if you look at this particular situation here, I will write this as d2 by dx2 integration of minus infinity to infinity. Excuse me, let's take the color code here. Minus infinity to infinity y and then dx, right? So that's just a rule that I can use here. And also I can write this as 4 and integration of minus infinity to infinity x squared. Let's stick with the color code here. X squared e to the minus x squared dx minus and integration of minus infinity to infinity. I'll put 2 outside, e to the minus x squared, and then we have dx here. Okay, now this is a pretty interesting situation, right? Because our suppositions of y was simply this: d2 by dx2 integration e to the minus x squared, right? So that was what we supposed as y, and you know that it's a constant, right? So we'll show that in the next step here. And we have here as 4 integration minus infinity to infinity, and look what we have here. This is the integration that we need here, right? And then this is minus, again 2 times whatever this is, right? This is just root pi. So that's what we just showed in the previous integration. Now we know that this whole quantity is 0, right? Because the integral here is just a constant, and we can just say that as a constant. So then I can just write this as 2 root pi equals to 4 integration of minus infinity to infinity. Now let us just be uniform in color here, dx. We only left with a single process now. Then I can say this is root pi over 2 is what we had to prove. Okay, so this is our final result here. So now what we basically did was we used some techniques to solve these integrations, right? So the previous one that I did was root pi equals to integration minus infinity to infinity e to the minus x squared dx. So that's what we did here. Okay, so that's it for today. Just a reminder here, we will be using this to results in the derivations of the average energies of the classical oscillator. So okay, so that's it for today. See you in the next lecture.